Okay, we're going to take a look at what we call absolute convergence and how we can prove convergence with root tests. Okay, so if we take the sum of the absolute value of the terms, if that converges, then we say that the original series converges absolutely. So it's important to understand what this term converges absolutely. That just means that the absolute value of the terms. So not definitely, really, actually, just it means the absolute value of the terms would also converge. And if a series converges absolutely, then the original series converges. So what this does for us is it allows us to take a series that might have some positive and some negative terms, and it often turns it into something that's a little bit simpler to deal with. And then we can make the conclusion that if we took the absolute value of the terms and it converged, the original also converged. Okay, so if we look at the sum of cosine of n over n squared, you can see it expanded right here. So here's where absolute convergence can help us. This isn't an alternating series, but it does have some positive terms and some negative terms, so we can take the absolute value. And we know that cosine of any number is going to be between -1 and +1. If we've taken the absolute value, it's going to be something between 0 and 1. So we know that the absolute value of cosine of n over n squared is less than or equal to 1 over n squared. And we know that the sum of 1 over n squared converges by p-series. So our original series converges by direct comparison. And since the series of cosine of n over n squared converges absolutely, we know that it converges. Okay, so here's the ratio test. Start with reminding ourselves of the geometric series. We have that common ratio r, and r can always be found by taking two consecutive terms and dividing. And we know that if the absolute value of r is less than 1, or if r is between -1 and +1, the series is going to converge. So we can relate some series to this geometric series, where if the common ratio is less than 1, we know it converges. Well, we may have a series where the ratio isn't constant, but if we're always multiplying by something less than 1, we know it will still converge. So if we take the limit as n goes to infinity of the ratio of the n plus 1 term to the nth term, and if that limit is less than 1, we know the series must converge. And if that's greater than 1, the series must diverge. And if it's equal to 1, it may converge, may diverge. The test would be inconclusive. Okay, we can look at this series here. Notice this series contains x. So x is a variable, could take on potentially any value. Here it is expanded. And we can apply the ratio test. So we take the limit as n goes to infinity. First, we increase n by 1, and we divide by the nth term, which is the same as multiplying by the reciprocal. And we expand and simplify. Take out x minus 5 because the limit is as n approaches infinity, which doesn't affect x. And so we get absolute value of x minus 5 times 1/3. And we know this converges if this limit is less than 1. So we can take 1/3 times absolute value of x minus 5. We know that that must be less than 1, which means x could be between 2 and 8. So x is a variable, and we've found that for any value of x between 2 and 8, this series is going to converge. So the radius of convergence is half the distance or half the width of this interval. So from 2 to 8, that's 6 units. The radius of convergence is 3. Now the interval of convergence, we need to check those endpoints because recall that this test is inconclusive if L equals 1. So we don't yet know if this series converges if x equals 2 or if x equals 8. We need to check those both individually. So if x equals 2, plug that in. And we can simplify, and we can see that this is going to diverge by the nth term test. So it does alternate, just alternates positive and negative, but n keeps on getting bigger and bigger. So we're adding bigger and bigger numbers, and it's going to alternate positive, negative, it's going to diverge. If x equals 8, this is just the sum of n, and this is just adding more and more and more numbers, diverges by the nth term test. So the interval of convergence does not include those endpoints. We go from 2 to 8. Okay, we'll take a look at another example here. Take the limit as n goes to infinity. Expand and simplify. Okay, so we can see that this limit approaches infinity for all values of x except for x equals 3. Because if we plug in x equals 3, we get, prior to the limit, absolute value of 3 minus 3, which is 0. So even though n keeps getting bigger and bigger and bigger, we always multiply it by 0. So we're just adding 0 plus 0 plus 0. So our radius of convergence is 0 because there's only one value for which this series will converge, and that value is x equals 3. So this was an example of r equals 0. If we ended up with r is infinite, that means the series converges for all values of x. So an infinitely large radius of convergence will encompass all values. Okay, now we'll look at the nth root test. So if we have a series with positive terms, we can take the limit as n goes to infinity of the nth root of a sub n, and that equals L. And the conclusion we can make here is the same as the ratio test. This converges if L is less than 1, diverges if L is greater than 1, and the test is inconclusive if L equals 1. So again, those are the same rules as for the ratio test. Okay, what's going to tip you off that you might want to use the nth root test is if you have something to the power of n. We can see that 2 to the power of n there in the denominator. So we'll take the nth root, and we can simplify that. And now let's go ahead and take the limit as n goes to infinity of the nth root of n squared. So we have to get a little fancy here. We'll try e to the power of the natural log of n to the power of 1 over n. We can bring that exponent out front. So this is natural log of n over n. We can use L'Hopital's rule because that is infinity over infinity. And that exponent turns out to approach 0, so we have e to the power of 0, which is 1. Recall that that was just for the numerator, so we have 1 over 2, which is less than 1. So this series converges by the nth root test. And here we have things switched around. We have 2 to the power of n on top. We already found in that previous example that the nth root of n squared approaches 1 as n approaches infinity. So we have 2 over 1, which is greater than 1. So this diverges by the nth root test.